All right, welcome to lesson 5. We're going to be talking about the product rule. As you might have guessed, we've talked about the rule for sums of functions, the difference of two functions, and now we're going to talk about taking the derivative of the product of two functions. So a student is trying to take the derivative of x squared, and their work is shown below. The derivative with respect to x of x squared, they then split up x squared into x times x, and then they take the derivative of each of these independently and then multiply them together. So the derivative of x with respect to x is 1, and derivative of x with respect to x is 1, multiply them together and they get 1. Is this work correct? Explain how you know, and what conclusion can you make about derivatives based on this example? Go ahead and give that a once over, write out your conclusions, and then we'll discuss. If we take a look at this work, we can spot the problem pretty quickly. The derivative of x squared, and you can tell this from many different vantage points, is not 1. Right, the slope of a parabola is increasing in both directions, and so it does not make sense that the slope of the function is always 1. And we know by applying the power rule that we've proven that the derivative of x squared is 2x. So what does this tell you? Well, this seems to tell you that if you are multiplying two functions together, and then you take the derivative of them, that you can't split it up in the same way that you split up a sum or a difference. Meaning, if you have a function of x times a function of x, you can't take the derivative of each independently and then multiply them together. Okay? And so what we need to do is look for a slightly different rule. And the way that we're going to do that is just like we've done for every other rule. We are going to use our limit definition to prove the general case so that we can then use it over and over again. A useful method for getting a conceptual understanding of the situation is taking a look at the graphical representation and then hypothesizing using the graphical representation. And in this case, we're not looking at any specific function, right? We're just thinking about any situation where you have some function of x times another function of x. And so in this situation, that will be slightly more challenging. But don't forget about that way of getting an intuition about any situation you're dealing with. So let's go ahead and take a look. All right, so the product rule of derivatives goes as follows. The product of two differentiable functions, u and v, is also differentiable. And, specifically, the derivative with respect to x of u times v, or the product, is equal to u times the derivative of v with respect to x, plus v times the derivative of u with respect to x. So what this is saying is that unlike the situation that we saw our friend trying in the discovery problem, you can't simply take the derivative of u and then multiply it by the derivative of v. You have this slightly different formula here. Another way of writing this is if you had two differentiable functions, let's call them f of x and g of x, then if you were taking the derivative with respect to x of f of x times g of x, then you're going to take f of x times g prime of x plus g of x times f prime of x. All right, so let's take a look at an example. In fact, let's quickly do the example that we just saw our good buddy try in the previous question. All right. So the derivative of x times x, and notice that I've written it, this is just x squared, but I've written it as x times x like our good buddy in the previous problem wrote it, so that we can apply the product rule. In general, when you can apply the power rule, apply it. it's going to be a lot easier. But in situations where we have some more complex things multiplied by each other, we'll want to use the product rule. So if we take a look at this, we can quickly identify the two functions that are being multiplied by one another, and what we can do is we can label them as u and v. So what we can say is let u equal x and v equals x. And I'm writing this out, I'm kind of doing a lot more work than you might want to in general, just to make sure you see how we're applying it. And so if we do that, then what we have is the derivative is equal to u times dv dx plus v times du dx. All right, well, u is just equal to x. Then the derivative of v with respect to x, well, v is equal to x, so the derivative of this with respect to x is just 1 times 1 plus v, which is x, times the derivative of u with respect to x. U is equal to x, so the derivative of u, or the derivative of x, I'm sorry, with respect to x is just 1. So times 1 again. And here I just have x plus x, which is, of course, 2x. And we knew that was the correct answer. All right. So hopefully that is a quick example that helps clarify the product rule. And now we can take a look at the proof. All right, not necessary that you take down the proof of this function, really just necessary that you watch, make sure that you believe that the proof works out, that it makes sense, and take note of the method by which this proof is done, because the goal is that by seeing these proofs, you're becoming sort of familiar with some of the tactics that you can take to mathematically manipulate things to make them work in your favor, so that you can see the meaning in the expression that is hidden there. So what I want to do is I want to let the first part of my theorem be the case, and then prove that what comes from it is what we've talked about. So the product of two differentiable functions, u and v, is also differentiable. I've just called them f of x and g of x here instead of u of x and v of x. So let f of x and g of x be differentiable functions, which means I could take the derivative of them if I needed to. And then by definition, the derivative of f of x times g of x will be the limit, as h approaches 0, of my function evaluated at x plus h. And so my function is f of x times g of x. So it'll be f of x plus h times g of x plus h minus f of x times g of x, or my function, divided by h. Now, if you take a look at this, you could obviously try substituting in 0 for h, and you get 0 over 0. So we need to think about some algebraic manipulation in order to make this work out. And what I'm going to introduce to you is a common method that is used to help us see some meaning where we can't initially see it. And what this strategy is where you add and subtract the same thing. And notice, if you add and subtract the same thing, you're really not changing the expression at all, right? If you have the number 10, and I say, hey, add 5 and subtract 5, well, you're going to end up with 10 all over again. And so what I'm going to do is I'm going to add and subtract something from the numerator that will be advantageous, that will allow me to factor in a way that is helpful, so that I can actually evaluate this limit. Okay, so notice that what I've done is I've subtracted from my numerator f of x plus h times g of x, and then I've added f of x plus h times g of x. So I've subtracted and added the exact same thing. So I have not changed the value of my numerator in any way. But with this little, I guess you could call it insertion, I have allowed myself to factor in a way that will allow me to evaluate each limit. So notice, if I take a look at these first two terms here, I can factor out an f of x plus h, which will leave me with g of x plus h minus g. over here I can factor out a g of x, which will leave me with f of x plus h minus f of x. All of this is divided by h, and so I can take each of these factorizations separately and divide by h, which we can, as we'll see in a second, is going to make everything work out just nicely. So what you'll notice here is I factored in f of x plus h, as I said I would, from these two terms, and factored out a g of x from these two terms. Now what I'm left with is f of x plus h times this difference here, and I can take this term and divide by h, and add it to this term divided by h as well. And then, when I do that, I can take the limit of each separately. Remember, the limit of the sum, or a sum of two things, is the same as taking the limit of each one and then adding them together. Similarly, notice that with each of these now split up, I also have a multiplication. I have a multiplication of f of x plus h times g of x plus h minus g of x over h. And so I can apply the limit property where the limit of two things multiplied is the same as the limit of one of them times the limit of the other. So I'm going to go ahead and split this up, and then we should be able to see how everything works out nicely. Alright, so here I've split them up and taken the limit of each of the factors, or f of x plus h, and then this piece here divided by h. So what we can do is now we can evaluate each of these limits. So let's take a look here. When I substitute in 0 for h, I just have f of x. So this here is just going to be f of x. Now notice what this is. This is the limit as h approaches 0 of g of x plus h minus g of x over h. This is the definition of the derivative of g of x. In other words, this is g prime of x. Now, over here, I have the limit as h approaches 0 of g of x. Well, there's no no h involved here whatsoever, so I can substitute in, and this will just be g of x times the limit as h approaches 0 of f of x plus h minus f of x over h. In other words, the definition of the derivative of our function f. So this is just f prime of x. And there we have it. The derivative of the product is f of x times g prime of x plus g of x times f prime of x. And so now you should, beyond a reasonable doubt, believe that that is how you take the derivative of a product of two functions. Alright, so let's do a couple of examples. So here we have a function f of x, and we want to find the derivative. Notice here that we have two functions of x multiplied by one another, and so I'll represent the first one I'll call u, the second one I'll call b, and I could write out and say let u equal this, let v equal this, and if you are at all feeling hesitant with how to use this rule, go ahead and do that, and I'll just show you how I would go through and solve it on my by myself. So I want to take the derivative, so f prime of x, and since I've memorized this, or if I'm a student just learning for the first time, I have this rule right in front of me. I know to take the derivative of a product, I need to take u, multiply it by the derivative of v, and then add that to v times the derivative of u. So I first have u, which is x squared plus 1 times the derivative of v, and the derivative of v is 3x squared, plus, this time I start with v, I have x cubed plus 3 times the derivative of u, which is 2x. And I can now simplify a little bit by multiplying these in. We'll see if we have any like terms that we can cancel, or combine. So this will give us 3x to the fourth plus 3x squared plus 2x to the fourth plus 6x. And sure enough, I can combine some like terms here. I will have 5x to the fourth plus 3x squared plus 6x. And that is my derivative. All right, the second one, I encourage you to try on your own, and I will put up the solution in a second so that you can check your work. Okay, so here I needed to figure out what were the two functions that I was multiplying, and I could see that I had square root of x times e to the 2x. And here I found it really helpful to clearly write out what each function was going to be. So u of x is the square root of x, and v of x was e to the 2x. And then before I actually go in and do the differentiation, I know that I'm going to need the derivative of u and the derivative of v. And so you can actually go find those ahead of time so that you make sure when you find the derivative of the whole thing, you're actually just plugging in expressions that you've already found. So the derivative of y with respect to x is going to be u, or square root of x, times dv, which is 2e to the 2x, plus v, which is e to the 2x, times du, which is 1 over 2 square root of x, and here I just simplified a little bit. All right, I'm going to put a couple up for you to try on your own. Make sure you have those ready to go so that you can present them tomorrow. All right, so go ahead and work through these three. Make sure you have a good solution, you've applied the correct rule, and you can present tomorrow.